functions, and it asks which is, or rational exponents, sorry, says which of the following is equivalent to 9 to the 3/4 power. So if you remember, I think we covered this way back in September, is we're going to get a little creative and we're going to substitute something that's equivalent to 9. Okay, 9 can be rewritten as 3 squared. So we're dealing with 3 squared to the 3/4 power. Then, if you remember, there are these certain powers of exponents that when you had an exponent that was raised to a power, it's called power of a power, we can multiply these. Okay? So when we multiply those, we get 6/4 or 3 to the 3/2. Okay, once again, we can do another thing since we have a fold as an improper fraction here. This exponent could be broken down into 3 to the 2/2 times 3 to the 1/2. Okay, 3 to the 2/2 just simplifies straight down to 3 to the 1st power. 3 to the 1/2 from your rational exponents you should know is a square root of 3. So our answer is going to be 3 times the square root of 3. And that's using all of your properties of exponents. First, we have to substitute in to get 3 squared. Then power of a power allows you to multiply those. That simplifies that down to that. Then at this point, we can split it into 3 to the 2/2 times 3 to the 1/2. 3 to the 2/2 simplifies down to 3 to the 1st. 3 to the 1/2 is a square root of 3. So you should get answer D. Okay, and once again, that's properties of rational exponents. So as always, just make sure I get those self-evaluations. When we were graphing just power functions, it wasn't necessarily the hardest thing in the world, so I don't anticipate too terrible of a response on those. Just make sure I get them by tomorrow. Those are going to be into the grade book tomorrow, also along with your lecture notes and your bell work from today. But looking at today, here are your new vocabulary. Okay, we have a polynomial function. We have a polynomial function of degree n. That's just a polynomial function that hasn't been stated the highest degree yet. The leading coefficient, the leading term test, a quartic function, which is a polynomial function with the highest degree of 4. A turning point, you guys are more familiar with those being called extrema points. Okay, where the graph goes from increasing to decreasing or from decreasing to increasing. Quadratic form, that is the form that you're most used to when you're talking about polynomial functions. That's where it's like ax squared plus bx plus c. It's what allows you to use the quadratic formula. We're going to talk about what happens when you have repeated zeros and multiplicity of zeros. Those are almost the exact same thing. So last week we were graphing monomial functions, or just power functions, which was x to the 6th, x to the 5th, x to the 4th. Okay, today what we're going to be doing is we're going to be looking at polynomial functions. So it still has a lot of consistencies, but instead of graphing just x to the x squared or x to the 3rd, we're moving it around, but then we're also adding way more terms. Like for a quartic function, it could be 4x to the 4th minus 3x squared minus 2x plus 1. Could be an example of a polynomial function. And you'll see that we're going to do a lot of factoring today to find the zeros. Desmos will be an option to kind of check yourself, but for a lot of it, it's going to be factoring. All right, away we go. So first types of problems that you'll have on your homework today is when we're graphing transformations of monomial functions. So from last week, we learned that this is x to the 5th, okay? It has a leading coefficient of 1 that's positive because it's not a negative. So this graph is going to start low, end high. It's to the 5th power because it's an odd degree, okay? But if you remember when we were doing parent graphs and parent transformations, we had an inside versus an outside rule. So that inside-outside still applies when it's in situations just like this. okay? This is going to be the graph of x to the fifth, but it's going to be translated to the right 3 units, okay? If it was minus 3 on the outside of the parentheses, then that graph would simply be just graphed down, okay, or shifted down. So we have horizontal translation, which is our inside terms, and we have outside translations or vertical translations as our outside terms. Okay, what you could do to graph this, we could just pick a series of points. I want to pick 3 to make sure that I have it, okay? I think you can do a good estimate of any function based upon 3 points, but to really drive it home, I want to think I'm going to pick about 5. So my f of x is equal to x minus 3 to the fifth. Okay, like I said, I'm going to pick 5 points, but what I'm going to do is I'm going to be real selective and real strategic about the picks, especially on a horizontal translation. I want to be real strategic with the points that I pick. I know for a fact that I want to pick one that is going to make my inside term 0, okay? Because generally that's going to be my y-intercept. So from order of operations, you know that we would take care of the parentheses first before we apply the exponent. So I have x minus 3. That means when I use the x value of 3, I'm going to get the value of 0. 3 minus 3 is 0. Now 0 to the fifth power. That's 0 times itself 5 times. That is going to be 0. Okay, like I said, I always like to find the term that makes that 0 because that's typically my y-intercept. Then from there, I'm going to pick my points. I'm going to go 2, 4, 5, and 1. Okay, when I plug in 2 minus 3 is a negative 1. Negative 1 to the fifth power is going to be negative 1. It's negative 1 times negative 1 is 1 times negative 1 is negative 1 times negative 1 again makes it the positive, and then multiplied once again makes it another negative 1. Key thing to realize is if you were multiplying a negative number, since we had 2 minus 3, that gave us our interior of negative 1 here. If it's a negative and it's to an odd power, your answer is going to be negative. If it's a negative to an even power, your answer is going to be positive. Because anytime you multiply a positive or a negative times itself, or a negative times a negative, you get a positive answer. So in this case, I'm multiplying negative 1 against itself 5 times. I know I'm going to have a negative 1. Okay, when I plug in 4 minus 3 is 1. 1 times itself 5 times is going to be 1. Okay, as you get farther away from the x-intercept, your math kind of gets a little bit more difficult, but it's nothing to be too afraid of. Okay, all these can be handled pretty simply on a calculator, or you can just write it out and do simple multiplication that way. When I plug in 1 minus 3 is a negative 2. Negative 2 to the fifth power is a negative 32. Okay, and what that's saying is that negative 2 times negative 2 times negative 2 times negative 2 times negative 2. If I wanted to write it out, I could do it that way. Negative 2 times negative 2 is a positive 4. Positive 4 times negative 2 is a negative 8. Negative 8 times negative 2 is a positive 16. 16 times negative 2 equals a negative 32. Okay? When I plug in 5 minus 3 is 2. 2 to the fifth power is 32. Since it's positive, I know it's going to stay positive. Okay, another couple things that you could realize is using the powers of your monomial or your properties of your monomial functions. Okay, if it's an odd degree, it has point symmetry. But for a power function, it was always about the origin, because that's where our x-intercept was, right? Here, we still want to have point symmetry. but we have to find out where that x-intercept is. That's why I always try to make my parentheses 0 first. Okay, now if you look at how my points compare as I move farther out, I go to a -1 when I plugged in 2, but I went to a +1 when I plugged in 4. That shows point symmetry. Okay, not origin symmetry because we're off of the origin, but it's always going to show point symmetry. Then -32 and a +32. Okay, so just a couple ways to make this very simple for yourself rather than having to plug it in, and carry out all the math. So, like they said, it had an inside translation of 3, and then it's just that graph of x to the 5th. So that is what our answer looks like. They started at 4. I don't know why they did that. A lot of their graphs in this section, they're counting by 4s. I hate it. But we'd have a y-intercept or an x-intercept here at 3. And then we would have those points that I built that table for. Okay, so graphing f of x, which is equal to x to the 6th minus 1. Once again, this one isn't a horizontal translation. This is a vertical translation. Okay, it's on the outside. There are no parentheses. So this is just going to be the graph of x to the 6th shifted 1 unit down. So if we remember from our power or monomial functions, normally we would have a x-intercept and a y-intercept at the origin. Since we're shifted down 1, the base or the extremal point on this graph is going to occur at 0, -1. Okay, and you can see it pretty here. Here's your extremal point. Okay, it's shifted down 1. The graph is decreasing from -infinity to 0, and then increasing from 0 to a +infinity with end behavior following your monomial characteristics that we covered last week. Okay, so graph f of x, which is equal to 2 plus x cubed. Okay, when it comes to a vertical translation, it does not matter if it is on the inside or the outside. Okay, if it's addition or subtraction, the order does matter. Since this is addition, we could rewrite this as x cubed plus 2. That way we get it in a format that's more familiar with ourselves. But it's going to be the graph of x cubed shifted 2 up. So from our monomial graphing, we know that x cubed crossed the x and y axis at 0, 0. Okay, it doesn't shift left to right, so our point of inflection, as you call it, is still going to fall on the y and x axis. It's just going to be 2 up, which is going to correspond to letter B in this case. So inside-outside translations still apply when you're talking to powers or the next section of graphing your monomial function. So that's how I think it's probably the first 6 questions of your homework are handled. Just real simple, real easy graphs like that. Single term, a monomial term that'll be shifted right or left, up or down. Okay, once again, the key is pay attention to where the addition sign is and where the subtraction sign is. That way you know if it's shifting left, shifting right, shifting up, or shifting down. Your inside are horizontal translations, your outside are vertical translations. Okay. This brings us into where we can carry those power properties or our power functions properties or monomial functions. We can apply them to polynomials, okay? More specifically for end behavior. Okay, when we said that our A value was positive and N was odd and we were graphing a polynomial function, we knew it was going to be a parabolic shape and that our N's were going to go either straight towards positive infinity or straight down towards negative infinity when you're talking about end behavior. Those are still true, but we're looking more towards the leading term. Okay, the leading term is the term with the highest exponent. The highest exponent. Okay, that has the greatest effect on the end behavior of your graph. All those other terms are responsible for giving you these turning points. Okay, but the leading term is what controls what's going on the very extremities of the graph. So it says the end behavior of any non-constant polynomial function, a(n) to the xn, okay? So we're focusing on n being our exponent here, can be described in one of the following four ways as determined by the degree n of the polynomial and its leading coefficient an. Okay, so when our degree is odd, our extrema are going to be pointing in opposite directions, very similar to the graph of x cubed, x to the fifth. Okay, and once again, we're talking on the very extremities of the graph. We can have multiple turning points, which you'll see, but the extremities of the graph are determined by the leading coefficient. So if the exponent of that leading coefficient is odd and the coefficient, the number that's out front, is positive, our graph is going to have this end behavior. Okay, it's going to start low and it's going to end high. So, or in other words, the limit as x approaches a negative infinity, f of x approaches negative infinity. And the limit as x approaches positive infinity, f of x approaches positive infinity. Okay, so now if n is odd, the exponent is odd, but the coefficient is negative, you can see it has end behavior where it's going opposite ways, but it's flipped. Our graph is going to start high but end low. Okay, so the limit as x approaches negative infinity, f of x approaches positive infinity, and the limit as f of x, or as x approaches positive infinity, f of x approaches negative infinity. So once again, when the exponent is odd, expect your graph to veer off in separate directions. If it's positive, it's going to start low, end high. If it's negative, it's going to start high, end low. Okay. So on the bottom left here, we have a even exponent. So it's talking about like x squared, x to the fourth, x to the sixth, and our coefficient is positive. So similarly with your monomial functions, the end behavior is going to go the same direction. If it's a positive and your exponent's even, the limit as x approaches negative infinity, f of x is going to go towards positive infinity. And the limit as x approaches positive infinity, f of x is also going to go towards positive infinity. Or in other words, your end behavior is going to go the same direction. Okay, that's any time that your leading coefficient has an even exponent, your end behavior goes off. It doesn't start low, end high. It continues off in the same direction. So bottom right corner, if we have an exponent that is even and a coefficient that is negative, once again, our end behavior is going to go the same direction. The negative means that it's flipped. So the limit as f of x, or the limit as x approaches negative infinity, f of x equals negative infinity. And the limit as x approaches positive infinity, f of x equals negative infinity. So it's the same terms that we use for our monomials. It's just they still apply when we're dealing with polynomials. Okay, but the key is it's all based upon your leading coefficient, or the coefficient that has the highest exponent. Okay, the highest exponent, that's where we're focused on. And that's in terms of end behavior. So it says, describe the end behavior of the graph of f of x, which is equal to 3x to the fourth minus x cubed plus x squared plus x minus 1 using limits. Explain your reasoning using the leading term test. So once again, our leading term is the one that controls our end behavior. It's going to be the one with the highest exponent, and we want to focus on the coefficient that's associated with it. So the coefficient here is 3 and it's positive. Our highest exponent is even. So that means our graph is going to be pointing up because the even coefficient determines that the end behavior goes the same way. The positive 3 states that they're going to go towards a positive infinity. Okay, so just by knowing that information, we have a good feel about what this graph can do. So the degree is 4 and the leading coefficient is 3. Because the degree is even and the leading coefficient is positive, the limit as x goes towards a negative infinity, f of x equals positive infinity. And the limit as x goes towards a positive infinity, f of x also goes towards positive infinity. So that's saying our graph is pointing up. It's that parabolic shape. It could have up to as many as 3 turning points and 4 real zeros, which we'll cover here in a second. So limit of f of x, that would be the answer when they're asking for us to describe the end behavior. Once again, it's coming straight from those properties that were in that chart. So describe the end behavior of the graph of f of x, which is equal to negative 3x squared plus 2x to the 5th minus x cubed using limits. Explain your reasoning using the leading term test. Here they try to get funky with you because our 2x to the 5th is not our leading term. Okay, or in other words, it's not out front. This, because it has the highest exponent, is still, this whole thing, this 2x to the 5th, is still what determines our graph's end behavior. Okay, we have the highest exponent with a positive coefficient. So our graph is going to start low, it's going to end high. So as x goes towards a negative infinity, f of x is going to go towards a negative infinity. And as x goes towards a positive infinity, f of x is going to go towards a positive infinity. So they can say that because the degree is 5, the leading coefficient is 2. The degree is odd and the leading coefficient is positive. The limit of f of x as x goes towards a negative infinity, f of x equals a negative infinity. And the limit as x goes towards a positive infinity, f of x goes towards a positive infinity. Okay, and once again, we're just describing end behavior. Okay, it's determined based upon our leading coefficient. So describe end behavior of the graph of negative 2x to the 5th minus 1 using limits. Explain your reasoning. So once again, we have an odd degree because our degree is 5, but we have a negative coefficient. So instead of starting low and ending high, this graph is going to start high and end low.
You need a break?
No, I'm teaching. They always do that. Like, come after 10 o'clock. Then I would love to have a break, but can't have a break till 10 o'clock. So because the degree is 5 and the leading coefficient is negative 2, the degree is odd and the leading coefficient is negative, the limit as x goes towards a negative infinity, f of x goes towards a positive infinity. And the limit as x goes towards a positive infinity, f of x goes towards a negative infinity. So in other words, our graph starts high, ends low. It's because it's a negative with an odd highest exponent. Okay, here, once again, we have an odd degree because it's x to the 5th. So we know our graph is going to be sprouted out different ways. Because it's a negative, our graph is going to start high. It's going to end low in terms of the negative 3. So because the degree is odd and the leading coefficient is negative, the limit of f of x as x goes towards a negative infinity, f of x equals positive infinity. And the limit as x goes towards a positive infinity, f of x goes towards a negative infinity, which is answer C. And once again, that's all just using the properties that are given in that key concept at the very beginning. Okay, here's the next key concept. Once again, it's always going to be centered around this leading coefficient, or the term that has the highest exponent. It says a polynomial function f of degree n must be greater than 1, has at most n turning points, or at n distinct real zeros, and at most n minus 1 turning points. So it's easier said with the example. This is coming from basically centered around the exponent. So it says let f of x, which is equal to 3x to the 6th minus 10x to the 4th minus 15x squared. Then f has at most 6 distinct real zeros. So in other words, the highest exponent that you have in that polynomial, you can have at most that many zeros. Okay, so if it's x to the sixth, you could have 6 distinct real zeros. That doesn't mean you are going to. Okay, it means that it is possible. Doesn't mean that you're guaranteed to have 6 real zeros. It's just saying, hey, you could potentially have up to 6 real zeros. Okay, then f has at most 5 turning points. So the highest exponent minus 1 gives you the amount of the turning points. So in this example, our highest degree is 6. 6 minus 1 is 5. So we could have 6 real zeros and at most 5 turning points. Graph of f suggests that the function has 3 real zeros and 3 turning points. Once again, when it comes to zeros and turning points of the polynomial function, it's all centered around possibilities. Okay, and you can look at the difference between these two graphs that I'm about to put on the screen. Come on, mouse. My mouse didn't want to come over here, it's scared. So let's say, for instance, we have 3x to the 6th. Okay, what it's just stated is that we could have at most 6 real zeros and 5 turning points. But if you look at that graph, it's just that parabolic shape. Okay, that's because our leading coefficient determines end behavior. It's all these other terms plus x to the 5th. Nope. Okay, let's get 1 minus x to the 5th plus 12x. Why can I not get a turning point right now? There we go. Okay. So if I zoom out here, once again, the leading term determined the end behavior of the graph. It's all these other terms that are responsible for your turning points. Okay, and you saw that when it was just 3x to the 6th. It was simply just a parabolic shape. But the more terms that are added cause more and more turning points. Okay, so the same way that a quadratic is determined where it's located by the plus bx plus c, polynomials follow that same trend. The leading coefficient determines how many real zeros are possible. The exponent minus that is how many turning points are possible, but it's not stating that you are going to 100% have those. And then this term is what's responsible for what's going on the exterior of the graph. This one, we had a positive 3 and an even coefficient, so our end behavior is going up. Okay, and that's more or less summarizing both of your key concepts. So, state the possible real zeros of the turning points of f of x, which is equal to x cubed plus 5x squared plus 4x. Then determine all the real zeros by factoring. So when you're looking at this, you're going to be factoring quite a bit. We're given x cubed plus 5x squared plus 4x. Okay, it's all set equal to 0 because we're looking for zeros. In terms of turning points and determining how many possible real zeros, all centered around the highest exponent. We have the 3. So that means that we could have 3 possible real zeros, 2 turning points. Okay, turning points is from this minus 1. Okay, but now it asks us to factor. So when you are factoring, the first step, as always, is going to be getting the greatest common factor out. In each of my terms, there's a present of x. So x can come out to the outside. Okay, that's the greatest common factor between all of my terms. Factoring out that x cubed turns into x squared, plus 5x squared turns into 5x, and plus 4x turns into 4. Now it's in a situation that's a little bit easier for you to factor. Okay, I'm going to be looking for two terms that multiply to equal a positive 4 that add up to equal a positive 5. So that is going to give me x plus 4, x plus 1. Once again, all separated into 0. This trinomial gets factored down here. Okay, remember we need to multiply to equal the constant, but we need to add up to equal the middle term. Okay, 1 times 4 is 4, 1 plus 4 is 5. Okay, at this point, we want to use the zero product property and solve for our zeros. This x on the outside still has to be factored in when you're using the zero product property. Zero product property states that any one of these terms or all of these terms could be equal to 0. Okay, so if we set all three of these, x, x plus 4, and x plus 1, equal to 0, and then solve for x, that's how we find where our graph crosses the x-axis. So first term, very easy. X is equal to 0. Okay, that means that we're going to cross at the origin. X plus 4, set equal to 0, and then solve for x. We would minus 4 on both sides to find that x is equal to a negative 4. That's our second 0. Our third 0 comes from x plus 1, set equal to 0. And then we solve for x to show that x is equal to a negative 1. The same way that we did it when we were factoring and finding real zeros and quadratic is the same way that we want to treat it here. Okay. At this time, we won't talk about multiplicity yet. Okay, but that's the zeros that we have found from factoring. And anytime you factor out a greatest common factor of x, remember it still has to comply with the zero product property. So most times when you set this to the outside, it means that your graph crosses the x-axis at the origin, or that you're going to have x is equal to 0. So the degree of the function is 3, so f has at most 3 real distinct zeros. It has at least 2 turning points. Once again, that comes from our highest exponent. To find all the zeros, solve the related equation, set it equal to 0, and factor. So they set it equal to 0. They factor out the greatest common factor of x. Okay, and then they factor the trinomial. Okay, to get those, then they're going to set each one of these individually to 0 and solve. That's how they got x equals 0, x equals a negative 4, and x equals a negative 1. And then we can always graph it to check. So this is what the graph would look like. You can see we cross here at 0, we cross here at negative 1, and we cross here at negative 4. Graphing is a good way to check yourself, but they expect you to algebraically solve all of these. Okay, one of the ways that you can factor that makes it simple for you is when you're dealing with a quartic function. Quartic function is a function that has the leading coefficient and exponent as 4. So and what it allows you to do, and typically you're looking for x to the 4th plus x squared. Okay? You look in this situation, you're looking for x to the 4th plus x squared. A polynomial expression in x is in its quadratic form if it is written as a times u to the 2nd plus bu plus c for any numbers a, b, and c, and a cannot equal 0, where u is some expression of x. So more or less, to put this into layman terms, we're going to nominate what u is. Okay, it could be x to the third, it could be x to the fourth. Okay, but most commonly we're probably going to do it using x squared. So if you look, this is the key that shows that we're in quartic. So x to the fourth minus 5x squared minus 14 is the example. If we were to write this in quadratic form, our u would be equal to x squared. So we could have u squared minus 5u minus 14 and plug in x squared here for u and substitute back and forth. So in other words, we're substituting in to get it into a quadratic so that it's easier for us to factor, because that's what we have the most experience factoring with. Trinomials that have a quadratic expression, the leading term of being x squared. So we're trying to take those possibilities and we're trying to substitute u in to make it easier for us. Okay, so if we're looking at this, this does fit the quadratic. Okay, u is going to be equal to x squared. Okay, and once we do that, it turns into a pretty simple one. So I'll write the original equation. That's x to the fourth minus 13x squared plus 36. Okay. So like I said, in this situation, u is going to be equal to x squared. Okay, so since u is equal to x squared, x to the fourth could be written as u squared. Okay, because x squared squared is x to the fourth, right? So then we have minus 13u, okay? 13 times x squared is 13x squared plus 36. So now looking at it, it's a whole lot less intimidating to factor. Okay, it's just fitting the form of a trinomial. We could factor this using the box if we really wanted to. Okay, but what we're thinking of is two terms that multiply to equal a positive 36 that add up to equal a negative 13. Okay, two terms that jump out to me are negative 9 and negative 4. Multiplied together, they will equal 36. If you add them together, they will equal a negative 13. So, and then we're going to write it like this, okay, still using u. So that's u minus 9, u minus 4. Those are our two binomial terms that are the factored representation of our trinomial. Okay, at this point, since u is equal to x squared, we're going to plug x squared back in. And we're going to get x squared minus 9 times x squared minus 4. Okay, then our zero product property happens back in. Okay, we're going to set each of these binomial terms equal to 0, and we're going to solve for x. So x squared minus 9 set equal to 0. We add 9 from both sides to isolate. So that's x squared is equal to a 9. Take the square root of both sides. So x can equal either positive 3 or negative 3. Because both of negative 3 squared equals 9, positive 3 squared equals 9. Doing the same thing on this side. X squared minus 4 set equal to 0. We add 4 to both sides to isolate our variable. We're left with x squared is equal to 4. We take the square root. And we're left with x plus or minus 2. X is equal to plus or minus 2. Okay, so looking at that, because our leading coefficient was a 4, that means it had 4 possible real zeros. It had 3 possible turning points. And our zeros are 3 positive 3, negative 2, and positive 2. Or answer A in this case. Okay, so that's the quadratic more or less. We're substituting in to make it easier for us to factor. Okay, we're substituting in to get it into a quadratic form so that we can factor it. Am I sharing my screen? No, I'm not. So here's the next one. I'm going to let the book walk you through this because I'm running out of time again. So state the number of possible real zeros in the turning points for h of x, which is equal to x to the fourth minus 4x squared plus 3. So highest exponent is 4. That means we can have 4 possible real zeros. That means we could have 3 possible turning points. Okay. 4, h has at most 4 distinct zeros and 3 turning points. This function is in quadratic form because x to the fourth minus 4x squared plus 3 can be rewritten as x to the x squared squared minus 4 times x squared plus 3. And we're letting u equal x squared exactly like we just did. So first step, they set it equal to 0. Then they substitute u for x squared. So x squared squared is x to the fourth. Okay, now they're going to factor that. So they're looking for 2 terms that add up to a positive, or that multiply to be a positive 3, that add up to be a negative 4. Okay, those are their 2 binomials that they got from factoring u squared minus 4u plus 3. So now they substitute x squared back in for u and set it equal to 0. Then they do the zero product property. Okay, the zero product property, or factoring it completely. They're treating it as difference of squares. At this point, you could set it equal to 0 and save yourself this step if you really wanted to. So our answers are going to be a positive square root of 3, a negative square root of 3, a negative 1, and a positive 1. Okay, at the step right before they said factor completely, you could set both of those equal to 0, okay, and then solve. And you would still end up with positive square root of 3, negative square root of 3. Okay, they just take it out. They're treating these two as a difference of squares. Okay. But like I said, when it's all said and done, you end up with the same answer. Okay, there's what our graph looks like. The degree is 4, has it 4 at most real zeros and 3 turning points. So when you're thinking about the quadratic, we're trying to get it into a situation that works for us. Okay, for this question, what we would have to do is first we would have to factor out the greatest common factor of x. Okay, that leaves x to the fourth minus 5x squared plus minus 6. So, and then we would, I'll just do it because I can't, I think this is a little bit heavier than what you're going to have involved, but one more example can never hurt. So we have x to the fifth minus 5x cubed minus 6x. So first step, we want to factor out the greatest common factor of x. So that leaves x to the fourth minus 5x squared minus 6. Okay, u is still equal to x squared. So we're going to substitute in u for everywhere we see x squared. Okay, this x is still there. So that's u squared minus 5u minus 6. Okay, and then we're going to factor this, looking for 2 terms that multiply to equal a negative 6 that add up to a negative 5. So that's u minus 6, u plus 1. We substitute x squared, and this is all still times by x. Substitute x squared back in for u, so we have x squared minus 6. X squared plus 1. Okay. Then we set each of these equal to 0. So x is equal to 0 is going to be one of our zeros. X squared minus 6 set equal to 0, and we're solving for x. So plus 6 from both sides, that gives you x squared is equal to 6. So x is equal to plus or minus square root of 6. Then x squared plus 1 set equal to 0. Solve for x by subtracting 1 from both sides. We get x squared is equal to a negative 1. Square root it. So x is equal to the square root of negative 1. You should realize that this is imaginary. Okay? So that means we can't have that 0. So what is that? Because the square root of 1 is an imaginary number. That means that those zeros do not apply to us. Okay? So our zeros are going to be 0 and plus or minus the square root of 6. Nothing changes in terms of possible turning points or possible real zeros. It's just that when we factored it and solved, we got an imaginary number. So most people you'd probably put like D, but that's an incorrect answer because it's the square root of negative 1, or the imaginary unit of I. So since those are imaginary, our answer is B. We only have 3 zeros, 0, positive square root of 6, and the negative square root of 6. Okay, and like I said, at that point, once you get it down to binomial terms, you can set it equal to 0 and solve. I mean, if it's perfect square, you can break it into difference of squares, but that's an added step that you don't necessarily have to go through. Okay. This one. This is when we have a repeated 0. Okay, it's also known as multiplicity of zeros. Okay, so anytime that when we're factoring, we come across the same factor more than once, that means that our graph does touch the x-axis, but it becomes what's known as tangent to the x-axis, or an extremal point falls upon the x-axis. Okay, our graph is decreasing, decreasing, decreasing. It barely touches the x-axis, and then it shoots back up. Okay, or it's increasing, it barely touches the x-axis and shoots back down. You'll see one here because we have to factor out the greatest common factor. So we have x to the 4th. X to the 4th plus 5x cubed plus 6x squared. Okay, the same thing that we did earlier, we're going to factor to solve and find our zeros. So all of this is set equal to 0. First thing we're going to do is factor out the greatest common factor, which in this case is x squared, because it is present in each one of our terms. So we have x squared. Once we take that from x to the 4th, that's going to be x squared. This is going to be plus 5x, and this is going to be plus 6. And then we're going to factor this trinomial to find our other zeros. Thinking of two terms that multiply to equal positive 6 that add up to equal a positive 5. I'm thinking of x plus 3 and x plus 2. 2 times 3 equals 6. 3 plus 2 equals 5. Okay, and this x squared is still here. Then the zero product property has to happen. So we set this x squared equal to 0. So x is equal to the square root of 0. plus or minus. Okay? This middle term, x plus 3, set equal to 0, solve for x. We get x is equal to a negative 3. And then x plus 2, set equal to 0. Subtract 2 from both sides to solve. We get x minus 2. Okay. So here, this is going to be a normal. At negative 3 is going to be a normal x-intercept. The graph is going to cross. At x equals negative 2, normal x-intercept, the graph is going to cross the x-axis. Here, this x plus or minus the square root of 0. Well, the square root of 0 is always going to be 0, and it can't be really positive or negative. Okay, that's an example of multiplicity of zeros. This is still going to be an intercept, but it is going to touch the x-axis and then veer back off. This is a multiplicity. Okay, or it's a repeated zero. Whenever we have repeated zeros, our graph comes down and touches that 0 and then veers back off. Okay, so it doesn't truly cross the x-axis. It becomes tangent to it. So they factor. Okay, of the zeros, x equals 0 is repeated. And you can see here on our graph, here's our 0 at negative 3. You can see it crosses the x-axis. Here's our 0 at negative 2. You can see it crosses the x-axis. Our 0 at x equals 0, it comes down, it touches, it becomes tangent, and then veers back off. Okay, that's what's known as a repeated 0. Also could be defined as multiplicity of zeros, which is what we were talking about right here. So, if x minus c to the m is the highest power of x minus c, that is a factor of polynomial function f, then c is a 0 of multiplicity. Okay, a 0 of multiplicity. M of f, where m is a natural number. If a 0 has odd multiplicity, then the graph crosses the x-axis at x equals c. Okay, so those are like your traditional x-intercepts. And the value of f of x changes signs at x equals c. If the 0c has even multiplicity, meaning that it's 2 squared, or like x squared, like we just had in the last example. Okay, x squared, when we factored it out, has an even multiplicity because it's x squared. You're thinking about the exponents. So if it's x to the 4th, that's factored out. X to the 6th. Those have even multiplicity. Then the graph of f is tangent to the x-axis at x equals c, and the value of f of x does not change. Or the value of f of x does not change signs at x equals c. Okay, so we got to think about the exponents that are associated with these. The problems that we're dealing with multiplicity here are going to be presented to you in this format. So it says f of x is equal to x times the quantity of 3x plus 1 times the quantity of x minus 2 squared. Okay? In other words, this is the factored form. Okay, so if we were to multiply this all out, we would get a giant long polynomial. Okay, but they're giving it to you in factored form. So what we could do, first, to apply the leading term test, we have to figure out what's my highest exponent going to be. Okay, so by doing that, we would have to multiply our x value through to find it. Okay, so the product of x times 3x plus 1 times x minus 2 squared has a leading term of x times 3x times x squared, or 3x to the 4th. Okay, so that's taking all of our 4th terms. And if we multiplied those all out, we would have 3x to the 4th as our leading coefficient. Okay, I just don't have enough time to really multiply it all out. When it's given to you in this format, you should be able to FOIL it pretty simply. Okay? Because we're down to the last 10 minutes of class, and this is the last concept we have to cover. So since it has a 4 as the exponent and our leading coefficient is positive, we know that our graph is going to have in behavior that points straight up. Okay, it's going to be a parabola that's up because it has an even degree and a positive coefficient. Okay, so that's what determines our in behavior here. So the limit of as x goes towards negative infinity, f of x equals a positive infinity. And the limit as x goes towards positive infinity, f of x goes towards positive infinity. Okay, for b, for f of x, which is equal to x times 3x plus 1 times x minus 2 squared, determine the zeros and state the multiplicity of any repeated zeros. So in this case, they want us to use the zero product property and set each of these equal to 0. So once we set this equal to 0, we're going to have x equals 0. Once we set this equal to 0, we're going to have x equals a negative 1/3. Once we set this equal to 0, we're going to have x plus 2, but the squared means that it has a multiplicity of 2. So our zeros are x equals 0, x equals a negative 1/3, and x equals 2 with a multiplicity of 2. Okay. And once again, they got all of these by setting these binomials equal to 0 and then solving for x. Okay. Now they're asking you to graph it. Okay. These are critical points for you. Okay. These are your x-intercepts. What this says, I'm going to share my screen. Stop sharing my screen so you can see the graph. What that says to you is that we have a 0 here that's going to be a traditional 0. We're going to cross. And then we're going to have a 0 that's a negative 1/3. It's roughly right about there. And it's going to cross the x-axis. We don't know. We know our end behavior. Our ends are going to kind of come up. And then at 2 from here. We know it's going to look something like that at this point. Okay, because our leading coefficient was 4, the 3 was positive, so end behavior has to go here. All we found is that we have a 0 at negative 1/3, a 0 at 2, a 0 at 0, and a multiplicity 0 at 2. So from that information, we could actually make a pretty decent sketch of this graph. Okay, at negative 1/3, we're going to be positive because our end behavior goes towards a positive 1 infinity. It's going to come down, it's going to cross, and then at x equals 2, our graph is going to come down, touch the x-axis, but then go back up. Okay, once again, this is just a sketch. I didn't plug any points in, I didn't do anything like that. This is the general shape that I'm able to access because I know what these things mean. I knew I had a traditional x-intercept at negative 1/3 with no multiplicity. So it's switching signs. Same thing happens at x equals 0. It's going to switch signs. My graph is. It's going to go from a negative to a positive. This 0 at x equals 2, since it had multiplicity, it's going to drop down, touch it, and then stay to the same sign. So that's a rough approximation of my graph. What they're going to ask you to do is select a couple more points to plug into this equation. And you want to plug simple, easy points. Okay? Because right there's, we have majority of the critical points. So find a few additional points. Okay, and they want to find that fall on intervals. So you can see from a negative infinity to a negative 1/3. Okay, that's above the x-axis because we had a 0 at -1/3. So they chose a -1. Once again, -1 is a pretty easy point to work with. Between -1/3 and 0, so where our graph dropped beneath the x-axis and is negative, they chose a -0.1, trying to find an easy point to work with there. I would probably use, yeah, that's probably the easiest point to use, looking at the equation. From 0 to 2, once again, this is where our graph is positive. Okay, we went from positive, now we're negative, now we're back to positive. So they chose a 1 because simple, easy point to use. And then after our 0, they've chose a 3. Okay, but we got the main points of that graph just by sketching it and knowing what's going on with our zeros. Okay, and they're just filling in points to finish it. Okay, and that's what our graph looked like. We had a 0 at -1/3 where our f of x switched signs. We had a 0 at 0, f of x went from a negative to a positive. And then our multiplicity of 2, 0, made it tangent to the x-axis. Okay, and remember that multiplicity determines whether it's even or odd. If it has even multiplicity, it comes down, touches, and goes back up. No change of signs. If it has odd multiplicity, it is going to cross. Okay, so here, this 1/2, it's going to be a straight cross, and f of x is going to cross the x-intercept. I just have 3 minutes, so I don't have enough time to go over it. They show a graph? Nope. All right, that's where we're stopping. I'm assigning the homework now. It comes from page 104 in the book, and it is numbers. Did I not create it? Oh, why did I type page 92? Dummy. God, that was dumb. You guys would have hated me for that. It's page 104, and it's numbers 2 through 42 evens. Okay, so roughly about 20 problems. Remember that they are due by Tuesday at midnight. Okay, Tuesday at midnight. I'll be available all day tomorrow. So don't be afraid to email me if you have questions. We can set up a Zoom meeting and go over stuff. I'll be here for your needs. But with that, we're about to go on break. So